Howdy, and welcome to the fourth video in the series on, you know what we're doing if you're watching this. Just kidding. This is reverted gear train design. In this video we're going to be covering more constraint functions, in particular the gear tooth stress constraints. Okay, so basically, we need to understand or build a model for what the stress on a gear tooth is. In order to do that, we are going to follow these equations. Oh, where are they? Right here. Okay, so this is the gear tooth stress, and this is empirical formulation. Has no basis in theory. Little basis in theory. Mostly, we just kind of figure this out, where we have all these different factors here that we get from different tables to calculate the stress in KSI, or thousands of pounds per square inch. Additionally, we can model the strength of a gear tooth. This strength SN in KSI as well, thousands of pounds per square inch. This one is based on the Bernal hardness number, which is basically a measure of, like, if you were to strike a material, how the failure surface would look, I guess. So these are strictly empirical. There may be better approximations out there, but these are the ones we're going to use. These equations come directly from the Fundamentals of Machine Component Design textbook, which can be found online for free. Go look it up. We're going to be in chapter 15, getting these parameters. So for instance, we have, let's see, let me find it. We'll have a table like this, number of teeth and Lewis form factor, and we'll figure out, based on the number of teeth and the pressure angle, what the parameter value is. Okay, so we're gonna do this like a bunch for all these different factors that we have to find for each gear. But in the interest of saving time and space, I'll just show you first what the stress formulations look like for this is a separate Python script that I've written. I'll provide it is a link in the description. So basically what I've done here is I've modeled each one of these factors. So say we have a graph that looks like this. What I did is I went through and I basically wrote down all these little points, the coordinates of these points, and the corresponding value of the function, and I fit bivariate functions to those approximations that I recorded by hand. So for instance, we have right here for the geometry, the 3D fit for the geometry factor, which can be found in figure 15.23a. I recorded those points, so we had an N fit and an N mesh fit and the geometry factor. So each one of these corresponds to a point on that graph by which I fit a smooth bivariate spline, which you can get from SciPy, interpolate. That way basically I could create this function that I would be able to call right here by putting in a gear pair. So basically a gear pair would be the number of teeth of one would be n, and then n mesh would be the number of teeth that it meshes with, and that'll give me the corresponding geometry factor. I'm going to make it easy on y'all by we're going to solve the worst case scenario constraint, so that we don't have to do all that smooth bivariate spline optimization, interpolation crap. So basically we can get the worst possible gear tooth stress for any gear and not have to worry about the exact number that it actually is, because that's what we do in engineering. We just pretty much make approximations all the time. So let's get into it. Here's a simple free body diagram of a gear. The force on a gear acts at an angle called the pressure angle. Generally this angle is about 20 degrees, but you will see gears that have pressure angle of like 25 or 14.5 or whatever. It just depends on the gear. So, but for this project we're going to be using pressure angle alpha is equal to 20 degrees. Now we also have a torque T acting on the gear in this fashion. We can transform that torque into a tangential force on the top of the gear by this relation. T is equal to the tangential force times the moment arm, which is the radius here. So using this equation we can solve for the tangential force, which is the torque over the moment arm, which is pretty trivial if you're an engineer or have any background in physics. That's pretty simple. Then we also want Fr, which is the radial force, or the force acting through the shaft and the bearing holding the gear in place. We can get that because we know from simple trigonometry that the adjacent over the, adjacent over, or opposite over adjacent is equal to tangent of the angle. So we have that here, opposite over adjacent is equal to tangent. So we have a radial force similarly calculated as Ft tangent alpha. Alright, now that we know this, the only thing that we're concerned about, we look at this because we want to find the gear tooth stress. The only one that from the free body that we need to determine is Ft. So we're not worried about Fr. So we'll go ahead and start by finding Ft. So let's go ahead and define the function now. Conf 19 model. Okay. Now, in the interest of simplicity, we're going to start with the first gear here, and we're just going to set these separate variables associated with the gear to d and n respectively, so that we don't have to type in model dot every time we want to, or every time we need to. So for this constraint, we're going to need d, n, p, and b. So this is a pretty nonlinear constraint function that is a function of pretty much every variable that we have. Okay, so now, first off, the torque on each gear is going to be different, right? Because, hold on, let's go, come on, here we go. Sorry, my computer is pooping its pants right now. Okay, here we go. So for each gear, each gear is going to have a different torque, right? Because, I mean, this input shaft, the torque is constant. I believe that we're going to be doing an input torque of, well, we're going to do 100 horsepower at 4,500 RPM, I believe. So since we're starting with gear 1, the gear ratio is 1 for 1 and 5, right? That's because the torque is not changing on the shaft from the input torque. So let's go ahead and put the ratio then is equal to 1.0 for this gear, which we're doing gear 1 here. So now we need the speed. We need to get the RPM here. Actually, I don't think we need the speed, so let's just not do that. So we have the ratio, so let's go ahead and calculate what that Ft would be. Tangential force, again, so we have the torque, right? The torque is going to be the input torque times, and before we jump into this, we'll just go ahead and define this. Input torque is equal to 1400.53333. That is in pound-inch. This is the torque that you will calculate if we are running at 100 horsepower at 4,500 RPM. 1400.5 pound-inch is the resulting torque, so that's what we're going to use. That's the torque. Okay, we need to multiply that by the ratio. Now, it's 1 in this case, so it's kind of trivial, but later on it's not going to be 1, so we have to take that into account now just to get the general way how it is. And now we need to divide, like I showed here, we need to divide by the moment arm. Since we have the torque, we need to divide by the moment arm. The moment arm in this case is going to be d divided by 2, because d is the diameter, so the radius is d over 2. Okay, so let's go ahead and define the pressure angle now. Pressure angle is, so we're going to use this degree to radian function provided by NumPy to convert from 20 degrees to radians, because that's what we use in physics. We use radians. So we'll start with the geometry factor. From here, J's geometry factor, figure 15.23. So in the worst case scenario for any given gear in the system, I figured that 0.3 is going to be a good approximation. It's going to make the stress the highest. So we'll do kV, which is the velocity factor now. And again, I'm just doing worst case scenario, so you can go and look at all the figures and determine for your own. But these are the ones that I'm going to do. Mounting factor, km, 1.4. And this is actually only true for idler gears, I believe. For regular gears, the teeth actually just bend in one direction. So if you think about it, for any given gear, the teeth are just going to bend in one direction, you know. They're going to want to move. They're going to want to bend with how the force is being applied. But if you think about an idler gear, it wants to bend this way when it comes up top, but when it gets down bottom, it wants to bend the other way because we have another gear attached down here that wants to push it the other direction. So the teeth actually undergo a lot more stress. So that's why we put this. It's usually 1 for any other gear, but for idler gears it's 1.4. So again, 1.4 is the worst case scenario. So and then we do CG, which is the gradient factor. CG is equal to 0.85. Again, this one depends on the diametral pitch of the actual gear, but 0.85 would be the worst case scenario. So that's what we're going to do. And then we need KMS, which is equal to 1.0, and I believe that one is this right here for two-way bending. Oh, okay. I messed that one up. So let's go ahead and just go look at what this mounting factor table 15.2. Okay, here we go. Mounting correction factor. Okay, so we see that in this equation, mounting correction factor is linearly is a coefficient to the rest of the equation. So the larger value, we're going to have larger stress. So we want to pick the largest one. So I think we say that our face width, we'll just take an average and we'll just put it as 1.4. So it doesn't really matter. So we'll just leave it as 1.4. It's fine. And here we'll just do 1 for KMS. I know we want the worst case scenario, but we're just going to do that because I think with all these other worst cases, even if we don't put this one at the worst case, it will kind of, they'll kind of cancel each other out. So we're fine there. So last but not least, let's do stress, the gear stress, and we're just going to go ahead and follow that function there that we had, E times J multiplied by kV times K0 times Km divided by 1000. So K0 is, I believe, is just 1. Yeah, overload factor is 1. And I divide by 1000 here because this equation actually gives us PSI and we want KSI. So divide by 1000. 1000.0 actually. Okay, and then we'll do gear strength. Sn times Cl times Cg Cs Kr Kt Kms. Okay, you'll see here that we don't have all those ones. So let's just go ahead, and Sn is going to be Bn divided by 4. We'll define Bn here in a second. And we'll do Cl. Let's see what that one was. The Cl is a 1, load factor. Kr, this is a reliability factor, 0.753. You can calculate a different reliability factor if you want. I believe this is for a 99.9% reliability, which translates to, I think, about 75,000 miles total if you drive like an average of 22 miles per day or something. So, yeah, and then CS is going to be, one second. Let me just figure something out real quick. This is the entire. CS is just a function of the Brinell hardness, so it looks like it's going to be 0.634. So I'll do that there, and then we'll put Bn here as 388. We're getting that from, we're going to be using AISI 4140 normalized steel, oil quenched, 25 millimeter. So these are the steel properties here. So we're going to be using, it's about 174.8 KSI and 388 for the Brinell hardness. So 388 KT temperature factor, just put that as 1. Okay, so now we have that, and so for the constraint, it's a stress constraint. So what do we want? We want the stress to be less than or equal to the strength. So return gear stress less than or equal to gear strength. Boom. Okay, so that's for gear 1. Now we got to do this 8 times. That whole process 8 times. So let's do that. And I'll just show you like the first 2, and I'll fast forward. You guys can do the rest yourself. So we'll do confun 20. Okay, so now this is for gear 2. Now gear 2, the only thing that changes here is that we have a different gear ratio. Okay, so we're going to have a different torque than we did on the first one. It's not just going to be 1. So we changed this ratio here. And this is going to be model.d. Let's see, this is going to be model.d2, model.d1. Okay, so that is the gear ratio. So when we do this over, so if we look at this diagram, we see that gear 2 is bigger than gear 1. So that means the torque on 2 is going to be greater than it was on 1. So if we look at that, we see that it just multiplies, right? So this should be greater than 1, this ratio. So that's it. That's all we had to do for that one. So the only thing that's going to change here every time is the gear ratio. So as long as you know how the gear ratio works, gear 3 is going to have the same gear ratio, D2 over D1, right? Yeah, because it's on the same shaft. So D2 over D1 means gear 3 is going to have the same torque as gear 2. It's just going to have a different radius, right? Oh, I forgot to change, because for this one, we're working on gear 2. Pitch 1, and the pitch and the face width is going to be the same as gear 1, though. But for gear 3, we're working with pitch and face width number 2. Okay. So actually I'll show you guys a couple more just so you don't lose your bearing here a little bit. So now we're going to be doing gear 4. Now gear 4 has the diametral pitch of 2, should be the same as 3, right? Yeah. So D2, okay, and then gear 4 is going to be a different ratio altogether. It's going to be this ratio multiplied by model dot D4 model dot D3, okay? So this is the total forward gear ratio. That's what we have for this gear. So that's all set. So we've gone through and done the whole forward, all the forward gears. So now we're going to do the reverse gears. 5, 5. Now 5 has the same pitch and face width as 1. This is 23. Now this ratio is actually going to be the same as it's going to be D5 over or D2 over D5. Okay. D5. Okay, so that's that one. Okay. Now we're doing gear 6. This has pitch and face width of 3. The gear ratio on 6 is the same as D2 over D5. Same thing there. No surprises. And that was 24. Only 2 left, and then we can solve the problem. 25. Gear 7. Now gear 7 is a slightly different ratio, model.d7 divided by model.d6. Okay, so that is gear 7. Last but not least, gear number 8. So gear 3 actually, or gear 7 actually has pitch and face width 3. Same as 6, 7, and 8 should have all face widths of 3. Okay. Okay, so this is just going to be model 8 over model 6. Okay, that's because we don't need to, like I said, this N7 cancels out, so we don't need to account for it when we're just getting the gear ratio across. So we just have this as the gear ratio. And this is function 26. Alright, so now we should have 8 separate gear stress functions that constrain the gear such that these variables make it so that the gear stress is less than the gear strength. So we have 8 of those for each gear. We have all of the pitch face width constraints. We have the center distance constraints, and we have the diametral pitch constraints. So, and we have the objective function. In the next video, I will be putting this all together, initializing all of those constraints into the model, and setting up the model so that we can solve the problem. We are almost there. So, with that being said, hope you guys are having a freaking fantastic time, and I'll see you next time.